Is Konrad Bajer. The topic of his presentation is
it's here.
there. Quantum vortex reconnections in collaboration with Kursa and Lipniansky, and Konrad's been known to all of us for decades at this point, so he needs no further introduction.
That's flattering at the same time. Thank you very much. And I don't think I should thank the organizers. Anyhow, and apologies to those few in this room who have already heard large parts of it, most of it, on some other occasion. But it's a short version, 20 minutes version, so it's going to be different in speed at least. It's joint work with Miron Kursa, who is behind all the simulations. He was a student, now moved on to working for a big computer center, and Tomasz Lipniansky, who's moved on to work on biological systems, but still keen on superfluids. And just very briefly, as the audience is mixed, this is all going to be about superfluid helium-4. So as it's called, the numbering is very confusing because it's helium-2, 3, 4, whatever, and they all A, B, and they all mean different things. But this is all about superfluid helium-4, so called helium-2. And the model, the nice thing about it is that you can go a very long way with classical model. So I can understand a fair amount of the dynamics of that medium without understanding anything about quantum mechanics. And there is the two-fluid model for helium-2, and the reason it was invented by Landau and Tisa. And why it's two-fluid? Because you do two experiments like this. One is pushing this fluid through a pipe, and it turns out that the flow rate does not depend on the pressure, on pressure head. So this is very strange, and it's like there is at least part of the fluid which does not feel any resistance when going through a pipe. And that part flows freely, whatever the pressure head. There is obviously a threshold above which the flow rate is constant. It's not accelerating without limit, but it's flowing regardless of the pressure head. And another experiment, you have a torsional oscillation or torsionally oscillating disk in it, and that's damped like a normal viscous fluid. So this is the dual behavior of like kind of inviscid and viscous. And this, if I understand correctly, led to the two-fluid model. And the essence of the two-fluid model, this is the simplest possible version with all dissipation removed from the equations. It's a mixture of one perfectly normal viscous fluid and one superfluid, i.e. fluid without any viscosity. And the curious thing, interesting in the superfluid part is that term, which is very unusual. This is something different from normal fluids, that you have force directly resulting from pressure, from temperature gradient. And that makes this thing very peculiar. So that mixture, what is that mixture? What is the relative density fraction of the two components? And it's measured in an ingenious experiment like this. These are very tightly stacked disks, and between them, the normal fluid, the viscous fluid, is locked. So when you can, by the oscillations of that torsional pendulum like that, you can work out the mass, and therefore you know how much normal fluid there is. And by doing this at various temperatures, you can measure the relative fraction, and it looks like that. There is a critical temperature, 2.17 Kelvin, at which it's purely normal fluid, and below that it's a mixture, and below about 1 Kelvin it's almost pure superfluid. And that term that I showed you, the force coming directly from temperature gradient, has very peculiar effect. If you put a heater inside that mixture and you try to heat it, then there is immediately force, and that means that the superfluid flows into the heater and it's miraculously converted, and normal fluid flows out of the heater. So that way you immediately generate, by applying heating, you generate what is called counterflow, the relative flow of the two phases. And there is, normally they wouldn't interact, but above a certain critical relative velocity, they do interact and generate vortices. And this is what effectively the mechanism, well, a similar mechanism, its relative velocity, is what gives the threshold for the flow in the pipe. Because when the superfluid accelerates to the point where the relative velocity between normal and superfluid component is above a certain threshold, the vortices are generated inside, and that gives mutual friction. And vortices, they look like this. This is a spin-up experiment, a cylinder. You look from the top, and you actually see vortices coming in. They are generated there. And so this is effectively a mechanism where, although when you spin the bucket, you accelerate only the normal component, and the inviscid part should be steady, should not feel any motion of the boundaries. But because there is some relative interaction, in fact, the superfluid spins up, and it gets vorticity, which normally would be smeared out, a uniform vorticity in the rotating solid body. The vorticity is quantized, but it gets enough of these things that effectively it spins like it should, being a normal fluid, but the vorticity is in a collection of vortices like that. And that's the way how they get into. They generated small loops are generated in walls, and their foot points move. One foot point moves to the free surface, and one foot point moves to the bottom of the container. And this is how they are generated. And quantum turbulence is when you have many of those already, you can drive it by the counterflow that I described before. These are simulations. And you can maintain, they interact, they flow, interact, reconnect, do all sorts of things. But turbulence, quantum turbulence, is that collection of vortices together with its dynamics. Each vortex, we have seen that before on Tuesday, has the dynamics that there are several levels of describing the dynamics of the vortex. One is the vortex filament approach, which means we take it's a line, but it's all classical, and there is motion in it's transported, carried by the superfluid component, and also it feels interaction. If there is counterflow, it feels there is a force in the normal component in the direction of the normal direction to the curve, and binormal. In the normal fluid, vortex moves in the direction binormal, but these vortices, they have a certain tension. There is force in the direction normal to the fluid. So if you have a vortex loop at finite temperature, it propagates like it should classically, but also shrinks. And that the velocity which carries it, properly within the classical approximation, properly is calculated from the Biot-Savart law. It's self-induced velocity. The vortex generates velocity which carries other parts of it, and also you can have external flow imposed externally. So this is a proper classical description, the Biot-Savart law, but of course you can approximate it by what is called local induction approximation, which means that we don't consider how distant part of the filament carries this one, but we also consider locally curvature and motion in normal and binormal. So this is local induction approximation, the local motion of this. And what I'm interested in, and is the reconnections of these vortices. When the two come together, they reconnect. For example, like here, there's one here and one here. They reconnect, and you get very sharp, very large curvature, a corner immediately after reconnection. And these reconnections are very important for the dynamics of the whole tangle, and generally they are important. So we are interested in what happens immediately after the reconnection. We cannot deal yet, well in a moment, with reconnection itself, because in bio-Savart, there is singularity there. You have to declare there is reconnection, it reconnects, but immediately after it separates, you can carry on with your bio-Savart or LIA, whatever. And that's what we do. So we start with a corner, with two half lines touching at coming with a corner, slightly rounded, like here. And this is the static configuration for the simulations. Well, first of all, there is a similarity solution for this configuration, and it was known before for the case of zero temperature. Alpha, coefficient alpha is a friction coefficient in that equation's there I showed you. The equation was known before for zero temperature, and Tomasz Lipniacki extended that solution to arbitrary temperature, arbitrary friction coefficient, which was very interesting. And this is the very interesting part. You have a similarity solution for the corner, which looks like a hairpin vortex with all these wiggles, except these are not waves, because they are just, because similarity solution, so it all increases in size as root t, square root of time. So they are not really waves that travel with their own velocity, but the whole pattern is increasing with time. But they wiggle, so they hairpin vortices, and as much hairpin as you can have. And these are for different temperatures. This is very high temperature, very large friction, so it's all very smooth. And when you go towards small temperatures, you get all these wiggles. These are LIA simulations, and gamma is the angle here, and alpha is that friction coefficient. So they are LIA simulations of one corner immediately after. Now, gamma is large here, and this is zero temperature. You see these wiggles. You see, first, immediately, you get a Kelvin wave going away, but then you see a Kelvin wave traveling away, but then these undulations remain, and these are not waves, these are just diffusive kind of thing. And it's a small angle, and you see the critical thing is that you see self-crossings. In LIA, self-crossings mean nothing because the two parts of the line are not aware of each other. But if they happen in LIA, we thought perhaps they happen in proper dynamics, so simulated with bio-Savart, and that's what you see. The self-crossings do happen, and therefore we declare at any self-crossing that it's another reconnection, because you have to declare that, and this is what you get in bio-Savart. So you have, for very small angle between these lines, anti-parallel, you have a cascade of loops coming. Okay? And the nice thing is that there is a critical angle. And in the LIA, that critical angle, if the angle is larger than critical, then no loops will be formed, no self-crossings. Below a critical angle, there are self-crossings. In LIA, that critical angle is about 8 degrees or 9 or whatever, and it's bigger in bio-Savart. So bio-Savart is better for self-reconnections than we thought, and we feared that alpha is the friction coefficient, function of temperature. And now, so LIA fine, bio-Savart okay. Now, so the ultimate test was to go to Gross-Pitajewski and see what happens. And this is what happens. It's more difficult calculation because you resolve the core. So you must start with lines which are close enough. You cannot have such a vast range of scales. So you see generation of loops. And in Gross-Pitajewski also, it's even better. The more faithful your physical model, the more that phenomenon of loop generation happens. In Gross-Pitajewski, you discover that even if you don't push them together, but start with a configuration like that, they come together first and then start generating loops. You don't even, so it's even more probable to happen. You don't have to push them together. And now is a speculative part a bit. You calculate the rate of line length loss. Loss meaning loss from that straight lines into the loops. And you discover that it's a geometric sequence both for times and for loop size. And the relation between these ratios of the two sequences is such that you get line length loss proportional to square root of time. So it's like diffusive kind of thing. And now this is all very idealistic. There are straight lines and this cascade. If it happens once to begin with, it will go forever, except the time separation between different detachments of loops. The next one will be longer and longer, but it will go on forever. Of course, you don't have perfectly straight lines. You have some curvature, large-scale curvature on this line. So you estimate when this happens to curved lines, what is the total line length? And the total line length you can estimate is critical angle times the radius of the large-scale curvature. So now, because all this is about how a tangle loses, it can lose line length, how it decays. If there is, in the limit of small temperature, where the effect of losing line length by friction is small. You do lose line length by friction when a loop goes and shrinks into nothing, that you lose line length. But this is for finite temperature. Now, what we have in mind is these small loops evaporating. Radiating away from the tangle. They generate an tangle by this mechanism. They fly through the tangle and get out and hit the walls, and you lose line length that way. Okay, so the tangle must be transparent enough. If it's opaque, you generate a loop inside, and it travels and hits other vortices and gets reabsorbed, and you don't have net line length loss. So you estimate the conditions for the tangle to be transparent enough to let these loops out all the way. So you have some criterion based on the size of the whole container and the density of the tangle. And when we try to see what is the line length loss by this mechanism, there is the classical equation for the line length loss, Weinen's equation, which says that dl by dt. L here, it's a little confusing because L has a dimension of meter to the minus 2. It's line length per unit volume. So it's not length. And it decays. dl by dt, this is not important here because that depends on counterflow. This is how counterflow increases, maintains the tangle, and this is how it decays. And this coefficient depends on temperature, but it's dl by dt proportional to minus L squared. Now in a transparent tangle, we get the same from our mechanism, except it's independent of temperature. That there is no coefficient here that would go to 0 with temperature. And there is also another mechanism being discussed at length. It's that reconnections pump energy into Kelvin waves. They generate these Kelvin waves. You saw them first, that you start with Kelvin waves. Yeah, and these Kelvin waves then dissipate energy by cascade, whatever. This is another mechanism, and the rough estimates that we have made is that for high temperature, you have the classical Wiener equation, and it all goes through mutual friction. For low temperature opaque, then the Kelvin wave to sound dominates, and you can estimate the range of parameters where it applies. And for low temperature and also very transparent tangle, that loop cascade mechanism would dominate.
You really need to show your summary, right?
Sorry?
You're over your 20 minutes. So
Oh dear.
I'm sorry.
I must be the first in this conference.
Yes. So you need to show a summary, and the next talk really has to get.
Okay. I'm afraid there's no summary to show.
Well,
Is that
okay. We can have further discussions
Yeah.
in the coffee.
Okay. That's
Take
it.
the speaker.
Shall I go back to the advertisement? Don't forget the proceeding.